All right. Good morning. Welcome, everyone. What Radiance workshop are we on here? 22nd Radiance workshop, unless Andy miscounted. Welcome to the tutorial session. I have not done a tutorial before. I think it will be glaringly apparent that I don't know how to do a tutorial. This is going to be more of a seminar. We're introducing some very new features in Radiance, and it's currently in alpha, so it's not even an official release. But we've had a lot of requests over the years for hyperspectral rendering, and people have found various workarounds. Some of them more elegant, some of them more painful, but none of them really optimal. So we're finally implementing this many years into, oops, sorry. And so it's new to me as well. And a lot of the stuff I'm presenting is sort of like, still haven't worked out exactly what an optimal workflow is. That's sort of going to be up to you guys to figure out. And I've just got some ideas at this point and some demonstrations. And this is more an introduction to hyperspectral than it is a deep dive. Counting is going to talk this afternoon and have a more traditional tutorial on his FRAD system, which includes some components he wrote for hyperspectral. I don't know if he'll get into those, but I will a little bit in this tutorial seminar. That said, please feel free to raise your hand, shout out questions at any point, interrupt me. Because we're not doing a hands-on, we have a little more air in the schedule, and you can use that to your advantage and ask questions, because that's going to be the best way for us to get through this material. As I said, it is brand new. So that said, here's a quick outline of what I'm going to talk about today. Start with an introduction and the context of hyperspectral, show some of the new Radiance primitives, well, all the new Radiance primitives that deal with hyperspectral, discuss the rendering parameters associated with hyperspectral rendering, and various other tools that have been added to support hyperspectral specifically, or additions to existing tools to support hyperspectral. And then we'll have an example scene with comparisons, before and after. And finally, we're going to get into a little more depth with the annual simulation methods and how to use hyperspectral sky data. So what is hyperspectral? Traditional rendering, as everyone knows, uses RGB to represent color values, and you can take that via 3x3 matrix to an XYZ color space. So hyperspectral rendering divides the spectrum into more than 3, typically more than 9 bands. And there you can change the spectral limits, so you don't have to limit yourself to the visible spectrum. You can go outside that to some extent. And it's more accurate and has new applications. So one of the impeti for this is that many researchers and practitioners are using rendering to determine melanopic responses, which have a different spectral profile than photopic or scotopic. And there's a distrust of approximations from using RGB coefficients. And then there's active research in terrestrial, solar, and sky spectra. And the current methods for handling hyperspectral, the workarounds involve multiple runs that often don't produce the same sample, so you get a lot of spectral noise. The advantages of native spectral rendering is that it's more efficient, since you're using just the one ray tree. You don't need to retrace anything. And as I said, retracing leads to chromatic noise. The new and then we also have a new native hyperspectral radiance format that works similar to HDR format, but has these extra samples in it. So here are the sensitivity curves for melanopic versus scotopic versus photopic. There's obviously a good amount of overlap, but the melanopic skews heavily towards blue sensitivity, as we know. And we can use these curves directly on a hyperspectral result to determine melanopic luminance. So the design of Radiance has these 3 component colors baked into all the material primitives. And if we were to increase that number, as I had originally thought I might be doing, that sort of breaks all scene inputs. So it's not a good solution. And part of the reason that hyperspectral has been so long delayed is it couldn't come up with a simple way to do it. I was contemplating initially extensions to the materials and geometry format, which already has spectral rendering, not hyperspectral, because it's just limited to the visible spectrum, but spectral rendering. But it would have required a full rewrite of the rendering code because of the different sort of modality of MGF and the semantics being so different from the traditional Radiance format. It would have been an interesting exercise, but one sort of beyond the scope of any foreseeable funding. Although the Radiance material types only support 3 spectral samples, we can introduce some new patterns that modify those materials in our hyperspectral. The idea is that you put this hyperspectral pattern on top of an ordinary material, and that material becomes hyperspectral, with some limitations as to what the pattern is, how it's interpreted for each material. So these are the new hyperspectral primitives that are introduced in this 6.0 alpha version of Radiance. There's the basic spectrum type, which is just a list of spectral outputs. There's a spec file, which takes that same list of per wavelength values from a file, a data file. Spec func is a programmable interface that allows you to change spectrum based on the user array parameters, like other function primitives. Spec data also takes data from a file as well as a function, and spec pict is analog to the color pict that loads this new HSR hyperspectral Radiance format. So we're going to be talking a bit about each of these in more detail. So depending on the primitive, it modifies a spectral pattern and is going to multiply the RGB color, either the transmission or the reflection, usually diffuse reflection. If it's metal, it won't affect the specular reflection. It sort of obeys the rules that are already established for patterns on materials. The multiplication rules against the RGB components that you provide in the materials is determined by a partitioning of the wavelengths that defines, sort of like the bands, the wavelength ranges for red, green, and blue. And it's a way that you can have some manipulation of the spectrum in the material primitive where it makes sense. A lot of times those RGB values will just be 1, 1, 1 to sort of like carry on the full hyperspectral. So these are the bands for this visible spectrum blown up here. Beyond 380 or so, we're in ultraviolet. Beyond 780, we're sort of in near infrared. And then there's, far infrared and radio, which microwaves, radio, we don't usually care about those. We often don't care about things in ultraviolet, but we do care about things in the long wave infrared, and we'll talk about how that's a bit problematic with this specification later on. The spectrum is partitioned into these wavelengths for red, green, and blue. 380 to 489 nanometers for blue, 480 to 588 for green, 588 to 780 for red. And this is for the purposes of multiplying against RGB colors that might be in the material. And that's just a simple way to deal with the fact that we still have these RGBs and they should mean something. And it's a way to sort of tune things a bit. Oops, skipped a slide. What happened there? The extrema may be adjusted to cover UV or IR, so you can move these endpoints so they don't have to be 380 and 780. And then the extended ranges get lumped in with the same red, and blue. The green range never changes. These wavelength choices may seem peculiar, but I did some tuning and found the ones that best agree with the existing RGB color space definition. So if you use those spectral ranges and you just plug in a block of energy into each of those ranges, you get out what is very close to our existing RGB color space. The actual maximum number of spectral samples is set by a compiler macro, and it defaults to 24 in the 6.0a pre-release. But you can change it at compile time if you have needs for greater resolution. So an example of the spectrum primitive is shown here. Obviously, we have a lot more than 24 samples that we've got over the spectrum. The code will take whatever you give it and move it into the rendering color space. So the rendering color space might just be RGB. So it'll take all those spectral values and just turn them back into RGB. But in a lot of cases, it'll be like 20 samples or so, and it will lump together as many as it needs to fit into each wavelength band. So here's the full spectral reflectance values for gold converted from the physical table with the complex index of refraction, not by Beam, by Andrew Glassner, I think. And then that just gets applied as a pattern to gold metal. So metal, as you recall, uses the color both for the specular and for the diffuse component, if any. This has zero roughness, 100% specular, so it's just all pure shiny gold. And then the 111 I mentioned earlier for the red, green, and blue just says don't modify the spectrum. The arguments are the starting wavelength, the ending wavelength, and then this is the count of samples plus. That just tells you how many samples there are and they evenly spaced in wavelength. And then, as I said, the 111 multiplies the spectrum, which in this case doesn't do anything. But if you had, for example, a different value for green, you put in 0.8 for green, that would get multiplied against the range for green, which I said earlier was 480 to 588 nanometers. So there'll be like a block of values that have 80% of what was put in. Yeah, Robert? No, but it only makes sense out to a certain wavelength if you're doing uniform steps. That's sort of the problem with uniform steps. Unfortunately, all the data is provided in uniform wavelength steps. So we're sort of like between a rock and a hard place, because the logical thing to do with wavelengths is to use frequency, because frequency is proportional to energy. So that way you don't have this blow up at one end and this long extended boring area at the other end, which is what you get with uniform wavelength subdivision. I mean, if you specify zero wavelength, that's one photon that has more energy than the entire universe. So that makes sense. So you really want frequency. And we're kind of stuck with this for now. Good question. Anybody else? You don't have to ask as good a question as Robert, but, questions are welcome. Yeah, David. That's true. You could bump up the max C-SAMP to 1,000 or something like that, and then have whatever 10 or 20 nanometer increments and still do the calculation. It would be extremely slow, and at the end, you're kind of wasting computation, but you could do it that way. So we can get some of our spectral data from existing MGF scene descriptions. At least I have a few of these that include spectral data. These were taken either from, this is a Macbeth color chart. So we have spectral data from Macbeth patches. So this is what the MGF description looks like for specifying a color in spectral values, again, uniform wavelength subdivision. And then it applies it to a material called blue flower color, a material called blue flower matte with a diffuse reflectance of 0.2. This gets converted by MGFT-RAD with the -S option to spectral radiance description. So here you can see sort of a one-to-one correspondence here, although this is, I think, in percent, so that gets modified. And all right. Doesn't look right, but it's supposed to be right. And then the 24% or 25% reflectance gets put into the RGB here. Oh, I know what. This is not properly normalized. This is normalized. So the conversion involves a normalization against luminance. So the new rendering parameters that go with spectral rendering, the most important one is the -CS parameter, which says how many spectral samples to use during rendering. And this defaults to 3, which means even if you have a spectral scene description, it's just going to do an RGB calculation unless you tell it to do more. So this can be set up to whatever the limit is for the compile, so 24 in the default compile. And then CW says the starting and ending wavelengths. You can give them in either order, but the wavelength range that you want to compute. So that defines the rendering color space, and then all the input is converted into that color space during rendering. Does that make sense? Yeah. Yeah, Alan, that's a good question. If you have, say, defined a material that you've only defined in the spectral range of 380 to 780, what happens if you're rendering outside that range? It all gets set to black, basically outside that range. It just assumes there's no reflectance or anything going on out there. And if you do a narrower rendering range, then the material is defined that chops off whatever data you gave it. Good question. And then there's some output color space options that are supported by rpict and rtrace, which is the -P option for pixel or primitive, whatever you want to call it. If you say -P RGB, just literally like that, it will output its standard RGB color space. So whatever spectral space it computed in, it will reduce to RGB in the output. It still can be more accurate than doing a straight RGB calculation, because every step along the way it was using spectral until the very end. So that way you get the interactions between the colored sky and the colored materials in your space. You just say, I don't care about the final spectral result, I just want RGB about it. I want to make sure it's correct. Similarly, you can specify an XYZ output, and if you're outputting a picture, it will output the XYZE common exponent format. So it's the same as RGBE, only it uses CIE color space. The advantage to that is that it covers the full visible spectrum, whereas RGB is limited to positive RGB, which means there are parts of the visible spectrum that get chopped off. And then you can specify any other RGB color space you want by giving the chromaticities in XY for the red, green, and blue primaries and white. rtrace in addition supports single channel output for photopic luminance with Y-PY, scotopic luminance with -PS, and melanopic luminance with -PM. Again, this is going to be take whatever spectral calculation you've done and apply the spectral sensitivity curve to get one of those 3 values. Or you can say, in the case of rtrace and rtpict, you can specify -CO plus, and that says output the full spectral computation. So if you've told it to do 24 bands, it will output all 24 bands. So instead of three values at each pixel, you'll get 24. And if you're outputting using if you're running rtpict, which is the version, it's a Perl script which runs rtrace in a way that's like rpict, it will output an HSR, one of these new hyperspectral radiance picture files. Any questions on this part? Good. Okay. The new our contrib and our flux matrix, which calls our contrib, always produce however many channels you specify with a -CS option. So it doesn't give you an alternative of converting color space. Since it's computing coefficients, which presumes you want those coefficients for something later on, it's always going to give you the full spectrum. You can, of course, run that through a filter like PCOM, which I'll discuss in a moment, that will reduce those to whatever other color space you want, but that's just the default behavior. So I'm going to talk a little bit about the new HSR image format. It stands for Hyperspectral Radiance and uses a similar common exponent encoding. So it has 8-bit per mantissa for each spectral band and then a common 8-bit exponent, which works reasonably well, at least with my tests. It's not as accurate as you might want, and we have alternative workarounds where you don't have to go through that 8-bit quantization. But the nice thing about this is that it works a lot like an HDR format, and you can even run pfilter on it and a few other tools. It won't display normally, other software won't recognize it like they do HDR, but it's a good starting point. I also was a little, learned from my years of experience that you should always look up a new suffix before you decide to use it, because there are so many out there, and people think they mean something or mean one thing when you want them to mean another. HSR fortunately wasn't taken. It's also very close to HDR. It's like one keystroke over. Be careful there. And yeah, that's it, I guess. So this new HSR format can be produced by rtrace. If you do the -FC specification, which would normally produce RGBE, you can get this HSR format out of rtrace. Also, our contrib, our flux matrix, or RT-pict will produce this. And it can be used by the spec-pict primitive I mentioned earlier. Quite handy for that if you have a spectral image that you're trying to get into your scene, or spectral pattern like the sky. This is Canning used this for Gen spectral sky, Gen S sky. So it's useful. And these files can be processed by pfilter, as I mentioned. There's a program called rcode to BMP. Probably nobody even knows about this, but it takes the new Radiance file formats for depth maps, ID maps, surface normal maps, and it, of course, handles pictures as well, and just converts them all to a BMP file for visualization. So it takes whatever you give it, that's this encoded thingy, and it gives you something that you can look at. So it's a handy tool to know about. RComb is a new program that's similar to like a mix of R matrix op and PCOM, which works on matrices or images, and hyperspectral ones as well. RCrop, which is a sort of very specialized tool for cropping matrices and images, and works with hyperspectral now, as well as, like I mentioned, R matrix op. So here's an example using RT-pict with RComb. So to make a hyperspectral rendering with RT-pict, you basically use all the normal RPict options, calling RT-pict instead, and then you have this -CS. Here I'm doing 18 spectral samples over the standard visible wavelengths, and saying -CO plus, which means I want the full color output, which means spectral in this case. That produces a hyperspectral image, which then I pipe through pfilter to do some anti-aliasing and then produce the final HSR image in the end. So very little changed. Really, you just added one option to get a hyperspectral result. And then if we want to look at a hyperspectral result, we could use rcode to BMP, like I mentioned. You just give it however many files you have and whatever formats they are, and it produces same named file with .bmp at the end. Or you can use the new RComp program and specify that you want an RGB output. This -C says convert it to RGB. -FC just emphasizes that you still want to use the common exponent format on the output, and then you get an HDR output. Or you can say, I want melanopic luminance, and I want it in a float format, and then it will give you a matrix with the same pixels in X and Y as float values. Any questions on this? Yeah, thumbs up. Okay. So now I'm going to get into a real example. Real example meaning really simulated. I have this scene that I developed in 2002 with Lena Eidelberg to do a rendering. Was it a rendering symposium then, or rendering workshop still? In paper on hyperspectral rendering and color spaces. So we have this scene with a fluorescent light and some Macbeth colors and this gold ball in the room in full spectral. These are the reflectances, the walls, pretty much neutral, perfect neutral gray. Here's the blue flower color is the more interesting one because it has sort of a magenta profile. Gold has this, where is it? This very low output in the middle. Anyways, it's got some interesting stuff going on, and more interesting is the nasty peaky spectrum of the fluorescent fixture, which doesn't show up very well in this graph, but hope you can see that. It's got a strong peak around 575 and another one around 425. So that will skew results quite a bit. If we do a straight RGB rendering and compare it to a hyperspectral rendering at whatever maximum samples, I think it used 81 or something, we get this kind of a delta E plot showing that we have errors as high as 15 or so, which is strongly visible. I mean, my rule of thumb is that based on experience, that if the delta E star is less than about 5, you can't really see in a side-by-side the difference. If you hold the patches near each other, then delta E star around 1 or 2 is where you can see a border between the patches. But if you've got 2 images side by side, you're not going to see it until around 5. So there's a lot of areas that are above 5. Green is 5, so everything, this whole wall has got visible stuff going on. This is kind of right on the border on this wall. But the lighting here is bad, so it's not going to be as easy to show this. If we compare the 81 spectral rendering to the RGB, what we mostly notice, it said green, this ball was really bad. What we see on the ball is it becomes it's a slightly duller or yellower green in the hyperspectral rendering, and it's also brighter in the RGB rendering. So that's the main area, is the difference in luminance. That's the main source of the delta E star area for that ball. Let me go back. There's also a lot of error here. That's probably just carryover from reflected error. You can also see there's a general tint change in the neutrals. There's also a saturation change in the red wall. We're also looking at it on a projector with completely unknown color behavior, so it's not the greatest comparison, but it shows that there are differences that are visible, at least in this example with the fluorescent light. We can compare it with different numbers of spectral samples. So instead of doing 81, let's try what happens with 6. 6 is a bad case. You don't want 6. So why is 6 worse than 3? That's an interesting question, and it has mostly to do with the fact that when you have 3 colors, you optimize those 3 colors to correspond to your cone's sensitivity. Whereas when you have 6, you're just chopping up the spectrum and going roughshod over it. So it really is much worse with 6 than with 3. Once you get to 9, you're down below, significantly below there you get with 3. So 9 is kind of the minimum recommended number of spectral samples. But there's no reason to stop at 9. 12 gives you further improvement, 15 further still. We're way below the side-by-side visible errors here, except for maybe the light source, which is understandable because it's not even really computable with delta E star. 18 spectral samples, we're down floating around, the patch visibility difference. So 18 is sort of the sweet spot, at least in this test scene. It's like there's no real need to go past that. In fact, it's hard to see the difference between 18 and 21 or 24. There's really no need for those extra samples. They don't cost you much, so you can still do them if you have that data, but it's not buying you anything. Calculation time. So this is just showing for this example what the calculation time is relative to number of spectral samples. So down here, starting at 3, we've got like 60 CPU seconds. And it goes up a little bit, but obviously we have a large, cost in just tracing those rays. The additional delta cost for tracing the spectral samples up to 24 is still less than 10 or 15% of the total cost. But, 80, if you want 81 samples, you are paying for that. So that's something to bear in mind. The other reason why the default macro is set to 24 is because it takes up memory. It takes up stack memory specifically, which is a kind of memory that's not as extensible as normal memory in a program. Because there are at least like 4 or 5 hyperspectral color members in the ray structure, and the ray structure is what gets built, what gets put on the stack when you make a call to trace a ray tree. If you're tracing a ray tree like 10 deep, then you have 10 times 4 times 4 bytes per float times however many spectral samples you've pile option. So even if you're only doing an RGB calculation, if we've said we want a limit of 81, that ray structure doubled in size. So you double the amount of stack space you require. And on some machines, if you get a stack overflow error, it's not a happy day, right? So that's why we sort of have this compromise. So I talked earlier about the concern with correct computation of the melanopic luminance. So a lot of times you may not care about what the RGB, what the spectral color is or even the RGB. You're just trying for a single value, but you want that to be accurate. So if you want to know the exact photopic luminance, you don't make a gray world and compute it as gray. You get the full spectral world and then you reduce the result to gray in the end, because that's going to tell you the right value. So this is showing just the error in, these are the photopic values that we get for this scene. And this is the melanopic luminance. And then this is the melanopic luminance estimated from RGB. And this is the relative error from using RGB instead of truth full spectral to melanopic. And you can see we are mostly on the high end. So we're overestimating melanopic luminance when we do an RGB calculation rather than underestimating, but we're overestimating by as much as 20% or so, which is significant in this scene. So things that we should discuss. First, the thing I pointed out that we leveled off at around 18 spectral samples, at least for this scene, at least for the visible spectrum. As we discussed with David and Robert earlier, if you're extending the spectrum to try to reach into the infrared, you probably need more spectral samples for an equivalent accuracy. So bear that in mind. As we said, we don't really see a benefit of spectral sampling until you at least get to 9 samples. There's no point in doing between 3 and 9. 4 would probably just be a disaster. That's not it doesn't prevent you from doing that, but it's not a good idea. The alternative approach, than the one we explored in the 2002 rendering workshop paper, is a different choice of RGB. So RGB, as I mentioned, is kind of tuned to our cone sensitivities, but not well tuned. You can pick a color space that's better tuned. It's called a sharpened RGB space, and the primaries are closer to the spectral locus, and they are also picked on wavelengths that correspond to sort of like the peak separation of your cone sensitivities. The cone sensitivities themselves overlap horribly. You don't do well if you just use cone sensitivities. You need to transform them into something that pulls cone sensitivities apart, and that's called a sharpened RGB space. And then we just did discuss extending beyond visible limits. So this is pulling back the slide from before, the error comparing 81 spectral samples to RGB. If we use this sharpened RGB space, we don't drop those errors to nothing, but we significantly reduce those errors, even though there's absolutely no additional cost because you're still doing 3 channels. So this is something that we suggested as a way to sort of improve color rendering accuracy with a standard rendering system, RGB rendering system. Because I didn't use that technique here. I was just swapping the RGB space and doing everything else the same. Yeah. But you're right. In the paper, we did this pre-multiplication of the source spectrum against the surface reflectances, and we got double the gains as still in a full RGB calculation. But that adds complexity. I've rarely used that method myself in practice just because it involves modifying the scene file based on the light source and things like that. So it's a kind of a hassle. Whereas swapping RGB space costs you nothing. It's just you change the primaries and you're done. Yeah, good question. Anybody else before we take a quick break? Rob?
Great. And I realize that it's very early stage.
Yes.
Right? Not from maybe a practical point of view, and I don't know how many actors have contributed their light source spectrum. But 4 years ago, they put out the standard format data, and I hope that at some point, IES to RAD and whatever this format is that they have will make it
seamless.
Well, get it into the workflow in a bit of a more fluid way.
Yeah, I'd love to see that. Yeah, that makes a lot of sense, especially for LED fixtures whose spectra can be wildly different. I think that's an important point. We're talking mostly about daylight here, but it's equally important for electric lighting, especially because that's our way to compensate in some situations for melanopic stimuli and stuff. Yeah, so good point. Thanks, Rob. Anyone else? All right. So just to give you an update on the schedule, we are going to finish early so you guys can get a head start on the hands-on part before lunch. So Tanning's going to take it over in an hour or so. Again, here is if you guys ask questions, so please speak up, raise your hand. All right, so now I'm going to talk a little bit about the spectral skies that you need as input. We have sources of spectral skies, including measured sky data and solar spectra. Or we could drive spectral skies from RGB data. It actually turns out RGB is enough with what we know about sky and atmospheric effects to do a pretty good estimate of what the spectrum is for a given RGB if you have well-calibrated RGB. But we'll also talk about using an atmospheric scattering simulation, which Cunning hopefully will cover in more detail in his talk Tuesday, tomorrow. How he does that, I don't know much about it. I just use the tools. So nice turnaround for me. So method one, spectral sky scan. There are scanners out there that will record full spectral sky patches. They tend to use 145 patches similar to Tregenza, but a different layout. The main difference being that the winding of the rows is different. So rather than being continuous and going around and then skipping the next row and going around the same direction. So here, I think this is from above, you see a clockwise winding. In the CIE method, there's a winding that is more compatible with a system that it goes around and then goes up a row and goes. So the different winding allows a sensor, if you can imagine having a cord or a limitation to its mechanism. It can't keep going around the same direction. It needs to go back, forth, and back and forth. And so the winding numbers end up being different and the data ends up being different. Why they can't just reorder it and make it say it's Tregenza, I don't know. They don't do that. So we have a new type now in Radiance for CIE sky position. This is a set of patch measurements. The actual file is very large. So this is a data file, but because it contains all these 20 spectral samples for 145 patches, that works out to a lot of numbers. Doesn't really matter. You just can't read it very easily. In addition to the sky spectrum, of course, we need the solar spectrum. And we can get that from sort of standard measurements. Kind of curiosity, the reason the solar spectrum looks like it does is there are a lot of absorption lines. So you have essentially a black body spectrum. Some of the light doesn't get through our atmosphere. It's absorbed by water and other gases. And those end up being little troughs here and there. And those are famous areas where the sky is opaque. I don't know what they all are, but derive a solar spectrum in whatever increments we want, and then we can just put it in a file and use the spec file type for the sun. It changes a little bit with the sky atmospheric conditions. Counting, actually, you compute that correct solar spectrum. In my examples, I'm just using the same solar spectrum no matter what the sky is, unless there's no sun. This is what the file looks like using the measured sky, and that's really not readable from where you are, I don't think, but here's the sun. So this is just values for the radiance of the sun. It gets combined with that specsun10.dat file using the spec file primitive. So that's the modifier on the sun's light source, and there's the sun in its correct position. And then we have a skyfunc, which is used, I think, just for the ground in this case. So this uses the standard GenSky output for ground. But then we have this spec data type that has that huge file of numbers for the captured spectral data using this CIE scan.cal to figure out that winding and everything for the patches. That gets applied to a glow for the sky. So here's the source for the sky, and then the source for the ground just uses the standard sky function because we don't have data for the ground. We just plugged in the numbers for GenSky. And then here we have our results for a skylight. This is actually just an opening in the ceiling. We didn't bother with glass. Sorry, Kristen. And you compare that to the RGB results, it's kind of hard to see the difference. There's not a lot of difference. In fact, in the delta E star plot, most of the differences in the areas that aren't completely blown out are below 7 or so, which means barely visible in a side-by-side. So in this particular case, even with the spectral sky, an RGB calculation turns out to be kind of okay. Any questions about this last part before I go on to the next segment?
Would that actually make a difference if there was like a wider lighting into the room? There's maybe still a little less.
So because of the sun patch being so bright, a lot of the illumination in the room is indirect from the sun patch. And so the sun, I think in this particular case, may be dominant over the sky. So that could be part of why there's better agreement, because the sun is close to a black body and doesn't have that much going on in terms of variation. I don't know. I'm speculating because I haven't done a lot of tests. Like I said, this is new for me too. So I'm just kind of going through the motions saying, can I do these calculations? Are they giving me the results I expect? Yeah. This stuff. It's primarily the quantization error. So there's a 1 to 2% quantization error in using the RGBE or spectral with common exponent. And if I do this in floating point, it's smoother. This which? Oh, you mean the sun patch? So the sun patch, that's a good question. I don't know the answer to that. Because it jumps from 1 to 8. I don't really pay attention to the sun patch because the way delta E star works, you have to have a white reference, and the white reference is pretty far below that brightness. So I don't even know what delta E star does when it's way out of range of the white reference. So I'd have to look into it more. It's a good question. I don't know why is going crazy there. I should probably block out all the areas that are significantly over the white reference point. To your second question, I'm pretty sure that's the simple translation that we just haven't done. To the first question, I could only speculate. I'm, like I said, new to this, and that's the kind of investigation I want you to do and other people like you to sort of like determine where are the sensitivities now that we have this tool. What do we care about? But we're also not very sensitive in the near infrared. So, I mean, sensitivity curves, even for the long wavelength cones, drops way down. So I'd be curious to see the results. So I'm going to do a deep dive at this point into the new RCOM tool. I personally love this tool because it sort of does stuff that our matrix op does, only better in some cases, and it also does stuff that PCOM does only better in some cases. So how many people have used, I mean, anyone's done annual simulations has been stuck using our matrix op at some point, right? Through hands, a few. Yeah, good. How many people have used PCOM at some point or another? More. This is good. So yeah, this is a tool that does row at a time matrix calculations. That's the easiest way to say it. our matrix op loads the entire matrix into memory and then loads the next matrix it needs to work into memory, does stuff, and then stores a result in memory, throws away the first one, goes on to the next one. So it's basically a matrix at a time calculation. And if you have a ginormous matrix, you won't have enough memory to even load it. So RCOM gets around that by doing just a row at a time. It comes with limitations. There's some operations like transpose where you kind of need the whole matrix. So RCOM doesn't do those. It doesn't do all the matrix operations our matrix op does, but it does a bunch more stuff because it's programmable. Similar to PCOM, you can have it do whatever you want with the matrix elements. So it uses less memory for the operations it supports. Like I said, it can't transpose, and it only concatenates two matrices. You can't have a long list of concatenations. And it's programmable, as I said. So you can have matrix and HSR or HDR input and output. So some useful options that it shares are matrix op, and some of these are new. The -C option used to be only for a coefficient list, and what it would do is it would take, because in Radiance, each matrix element has n components, usually 3 for RGB, and you can think of those as stacked matrices. Like when you're doing the operations between RGB matrices, it's like you have a red matrix operation followed by a green matrix operation followed by a blue, but they're done at the same time. So it's just like these parallel matrix operations. There's no intercommunication between channels except via this -C, which says, I want to take my single element, however many coefficients it has, and multiply it by my little matrix that I'm giving you, which can just be, for example, if you're going from RGB to photopic, you would just have 3 coefficients, and it would take your RGB and put it into one channel. But if you wanted to say, transform those 3 RGB coefficients into XYZ, you would give it 9 coefficients. And then you'd get 3 channels in, 3 channels out, but at different channels. So this is a shorthand that's new, where instead of a coefficient list, like if I wanted XYZ from RGB, I'd have to before give 9 coefficients. Now I can just say -C XYZ. And it puts in the 9 coefficients. So it will take us a symbolic specification of a matrix or a vector. You can also tell it to grab stuff from a file. So if you say, I want the color space to be the same color space as this other file I have over here, it will load the header for that file, look up the color space, and try to get into that color space. So it's a convenient that didn't exist before. The only difference between the lowercase c and the uppercase c is the uppercase c says, not only do I want you to use this set of color space for the following matrix, I want you to use it for all the matrices that I'm giving you from here on. So it's just a sticky setting. Show you why that's useful later, maybe. The scales coefficients, and then the -F, as usual, specifies the output format. So it can be ASCII, which is or float or double, or the common exponent format, which is given as C. The default is to use whatever is from the input. So if the input has 2 float matrices, you'll get a float output. And it sort of like upgrades to whatever the highest res is. So if you give it an RGBE input and a float input, it will output float. If you give it a float and a double, it will output double. It's best to specify it if you have something in mind. So there are some options in RCOM that are similar to PCOM, -F to load a cal file, -E to have it specify an expression. You can turn off warnings. You can trim the header. It doesn't get rid of the header on that output. It just keeps it from blowing up. So if any of you have had this experience where you've run a bunch of PCOM operations or decompose operations, it takes all the headers and it adds to the headers, and at some point you have like a 1 megabyte header. So this just says, I don't need all that previous stuff. So unique options to RComb, you can specify a matrix for concatenation that gets applied at the end. Like I said, you can do one concatenation, and it's actually really common that you will do one concatenation with RComb. You can specify a number of processes to run. And this was actually really hard to implement. It took me almost 2 weeks to implement because it's very tricky to do on some operating systems. But it basically starts a number of processes and does rows in parallel. It's more or less linear speed up that way. So how do you use the expressions in RComb, and how is it different from PComb? Since many of you have experience with PComb, it's a similar kind of concept where you're specifying what the output element should be based on input elements. But because there are more options for how many coefficients can be in the input elements, not just 3, it complicates the standard variables and predefined functions a little bit. You still have number of files for the number of matrices or pictures or combinations of matrices and pictures on input. There's a number of columns and a number of components, and these have to sort of be matched up between matrices. So by the time you get to the expression evaluation, you have to have the same number of columns and the same number of components for it to work. Number of rows is also usually available, but it could be 0 if it's unknown. So that RComb, unlike other tools, has the ability to handle infinite rows in the input or unknown rows on the input. And that's because it goes a row at a time. R and C are the current row and column, starting at row 0 at the top. And then CI is how you access the actual coefficient. So it's component P of input I at RC. So you only have access to the current row column that you're working on in your script. And then you can also ask, what is the wavelength? And this is a constant function. What is the wavelength for component P? And it will give you the central wavelength for that component. So that's obviously mostly useful for Hyperspectral. And then these are the functions and variables that you define to specify the output. So similar to PComb, you can have CO, which is the current component output. So you can specify a very simple expression that's then applied to each component and done the same. So it will take that component's input and do whatever you say and produce that component's output. So that's a simple one-to-one. You can also specify which component you want. So you can have, the red component adding to the blue or the green if you're trying to change color space or whatnot. You can use these ROGO similar to PComb, and that works for RGB output, but you don't have to. If you don't specify CO, then the output is a straight sum of matrices that haven't otherwise been dealt with, similar to PComb. I should ask any questions on this. It is a little bit obscure at this point. This is kind of the place where hands-on would be helpful, but don't really have time to do it. So typical usage for RComb, a very simple example. If we want melanopic output for the sum of 2 or for the ratio of 2 matrices, we say RComb, convert everything to melanopic luminance. Here's an HSR picture, so however many spectra in there, reduce it to single channel melanopic. Here's an RGB picture, an HDR image to convert that to melanopic also. And then they would just give me the second melanopic, which is view1.hdr divided by the first one, view1.hsr. So this is basically telling us ratio between these 2 images in melanopic luminance. And I said -FF to get floating point outputs. So here's one where I'm applying a specific set of spectral weights. So let's say I have an atrium and I'm trying to figure out how much photosynthesis I'm going to get out of my plants. I would have the plant's sensitivity function that I apply to the spectral image or whatever, fisheye image, and then convert that result to some kind of RGB that I'll visualize, for example. So the easiest thing is to do it like this, to put it in a file that you name, and then you just drop those onto the command line with this is command output insertion for those of you who are not Unix savvy. So the back quote just says, take the output of this command, which in this case just spits out that file, and put it on the command line for me. There should be easier ways to do that. Melanopic is built in, but if we have other things that end up being so useful that we really want them built in, yeah, we can build those. Malika? Yeah. Yeah, so it uses, well, I'm trying to remember it. Because there was some confusing definitions and I chose one, and I ended up choosing the same, I think, for the use of the photopic conversion factor, luminous efficacy, whereas the scotopic one traditionally has this weird definition where it's the crossover point. So here's a more challenging application of RCOM. I had this idea several years ago working with Lars Grob to use the holodeck in an annual simulation. So those of you who aren't familiar with the holodeck, it basically computes rays in a room and allows you to free move around and computes new rays. You can also pre-compute a holodeck and it will sort of capture all the rays flowing around in the space, all the primary rays. And this is a way to substitute those primary rays for a different set based on different sky conditions. So we use our flux matrix to take the rays from a holodeck and figure out how they relate via a matrix to the sky patches, something like that. So that's what this first command does. RHCopy takes the rays out of a holodeck, spits out the origin and direction, which is what our flux matrix uses to compute a daylight coefficient matrix, which is really long and has many, many rows in it, because there are many, many rays going in, and uses the Tregenza sky description and the scene description that's associated with that holodeck. And then we can run RCOM for a particular sky and replace the rays in the holodeck. So you start by creating an empty holodeck using a template that corresponds to this original holodeck. And you specify that at the same time the octree for that other sky condition in case you're doing a live calculation. You use GenSky for that sky condition, send it through GenSky Vect to get a vector out, and then apply that vector, which is a matrix input. That's what the dash means, is read the concatenation matrix from standard input and apply it to the daylight coefficient matrix and output floating point RGB in this case for each ray, chop off the header, and then laminate those new values with the origin and intersection point of the original holodeck. So it's this weird thing where we're just trying to we're in the holodeck with a new set of values. And RCOM is critical here because if you try to give this matrix op or something and it tries to load the matrix, it's like 50 gigabytes. It's just not going to work. So it's doing this on the fly, row at a time, doing the matrix multiplication against the new sky, and then putting it using RLAM, which just pastes together rows of data. In this case, floats for the values read from standard input, and 6 floats for the origin and intersection points. That thing gets piped into another RH copy, which puts the results into the empty holodeck. So it says take input, value, origin, intersection point, floating point format. Don't worry if they're unique. Don't look for duplicates, basically. So this is a way to reload the holodeck with new data. And it's a little bit clunky, but in the end, you can then drop into your holodeck and it's the new day that you substitute. So the idea was to use this for glare calculations, things like that, where you want to look at it over many, many viewpoints, many times a day. So it's similar to what Stefan Wasilewski was doing, but not as fast. Not with all the advantages his method has. Any questions on that? All right, so now that we know a little bit more about RCOM, we're going to see it applied in some other methods. So this is where we're taking RGB captured skies, and this is using Chris Dumon's SkyCam and data that Andy provided me, which is pretty good calibration with RGB. I did some checks against raw capture of Macbeth chart under known illumination, and actually the processing that's done in the library that Chris is using does a pretty faithful job of getting RGB, which is important because if you have good RGB data for the sky, you can figure out what the spectrum, what corresponding spectrum that sky has. So we used a method from Pritham et al. To create that spectral sky from RGB data. So first we convert to XYZ, and that's the same as XYY really. And then we convert that data to these 3 coefficients, which correspond to sky components. You'll see the curves for those in a second. They're essentially, I think, like a principal component analysis of sky, And then we use those coefficients in a linear combination of these standard components. So these are the standard components. So we have sort of a base component. This is equivalent to like the DC component of skies, the average of all skies. And then we have the 2 variants for shifts in the sky due to aerosols and things like that. I don't really know the details, but because it's like a PCA, you know that you can tweak these values and come up with just about any sky spectrum, any sky patch spectrum. So how is this done? Here's the RCOM command. It's kind of nasty, but it takes it's going to produce in the end an HSR image for the output. So that's what this -FC is. We're going to start by converting the first input to XYZ coordinates. So that's the first input. It uses the SkyFact.cal and the Sky2Spectra.cal to do some conversions for us. And then it has this color conversion matrix for the XYZ. So the color conversion itself is also computed for 20 spectral samples using RCalc and the SO, S1, and S2 functions that are defined in SkyFact.cal. So we send 20 samples through this RCalc command. That's really quick. And it spits out 20 coefficients that are, spits out 60 coefficients, one for each of these sky component channels that are applied as a matrix to the XYZ coefficients that we got here and converted. And And then we just add the wavelength splits, which has to be, I should have talked about this before, has to be in the header for the file to make it a standard HSR file. And then here's what's in the spectra, the sky to spectra.cal. I don't expect you to understand it. I don't understand it myself. I forgot what exactly happens here, but it essentially takes those curves I showed you and does some normalization against the photopic sensitivity, which you need to do to get these things to balance. So we have the input Y, which is the first image, second component. So we've taken this image, we've converted it to XYZ. So that becomes the second component, and the first image is just the Y channel. And then to get the little X and little Y channels, we just take in the case of X, we take the X channel, which is the first input, first component, and divide it by basically X plus Y plus Z. And similar for Y, we take the Y and we divide it by X plus Y plus Z. So those are little X and little Y. That's just the standard definition. And we use M1 and M2 functions, which are taken from Pritham et al., which are just little conversions that take the little X and the little Y, and they give you the coefficients for that sky path. This multiplier, as I said, is for normalization. And then the output, CO, for channel N, is first, if the Y is very small, just spit out 0, because you're dividing by Y, you've got to be careful about that. And where Y is non-zero, then we select either a coefficient of 1, or the coefficient for M1, or the coefficient for M2. That was clear as mud. Yeah, so the S0 coefficient is always the same as the multiplier. The M1 coefficient has this additional thing which is basically just a little matrix vector multiplication, and in M2, same for that second little component. So we have the DC component and then the two other curves. And those get combined. So effectively, it's taking your RGB sky and it's giving you a full spectrum based on based on the spectrum for any given mix. That makes sense to you? So you have these curves. Any given mix of these curves will give you a lowercase x, lowercase y chromaticity. So you can do the reverse calculation and go from the x little y chromaticity to what the mix should be. Get that? And that gives you the full spectral sky. And it's really accurate. It's actually surprisingly accurate. It's within a few percent in most cases. And Tanning pointed out this paper. Thanks to you. Correct, because we have an RGB fisheye image. This gets applied to an HSR image. I'm trying to see. So we have the description here. So the output of this whole thing was this specsky.hsr, which is a fisheye image with per pixel, not per patch. I was saying patch the whole time, but it's really per pixel spectrum. And then that gets applied in a spec pict over here. Gen sky modifier, Gen daylit modifier skyfunc. So it's doing, but it's a spectral pattern. HSR file and applies the fisheye mapping to get directions mapped into pixels. And then on top of that, we have the solar spectrum for the solar source. And that's the whole thing. And then it's just a standard sky, 180-degree sky. That's the whole description. This is really fast to compute, and it works really well if you have SkyCam data. So I highly recommend this method. So here's the results. This is using spectral compared to RGB. Again, kind of hard to see the difference between those two. And if we do The delta E star, we see again, the errors are pretty low except in the sun patches where we can't really account for delta E star anymore. But we're down, most cases, pretty low differences. So I was kind of surprised by this. I was hoping to see more differences from the spectral calculations than we saw. We see it mostly in cases where the light sources are a little peculiar, and I think that's to Rob's point. We should get some LED data in there to really see what happens. Yeah. That's how many Tanning chose to use, and that's how many a lot of the data is provided. It's just it's like 20 nanometers increments, 20 nanometer increments over the visible spectrum, so it just works out to that number. There's no particular reason for choosing that otherwise, but I think all of Tanning's tools use that breakup, so it gives you more of a direct translation. Because otherwise you're resampling between different wavelength bands and can introduce some quantization errors doing that. Generally speaking, you're okay having too many samples. If you hit it with 80 samples, just throw them in there and it will reduce it. But if you have in one case 9 samples, another case 12 samples, another case 11 samples, things might start getting messy. All right, so the next method I'm going to talk about is using daylight coefficient spectral skies. We can convert the RGB sky captures to column vectors, and then run our flux matrix to create a spectral vision or measurement value matrix, and then combine RCOM with R split to get out the time step HSR pictures. And then we'll show how to apply a post-processing to simulate electrochromics. This is a little bit messy. Normally this would be done by DC time step, but DC time step is not currently, nor will it likely ever handle hyperspectral. So, and there are reasons for that. Mostly having to do with the way that it's coded and the efficiency. To get from the sky capture to a matrix, we don't really have good automation for this step because of the sun primarily. If you don't have the sun, then you can use our flux matrix and it's pretty easy. But if there's a sun, then you kind of have to find it where it is and which patch and integrate its value and so on. So we need something like GenSkyVec that works with spectra, and we might improve GenSkyVec at some point to work with spectral data, but right now we don't have it, so we have to do this manually. But Tanning has this new tool that will take a weather tape and generate spectral skies called GenS Day Matrix, and I'll have a quick example of that later on. So the spectral value matrix is the same. It's just the same command with one additional option to standard R flux matrix. So you use VW rays to generate the pixel sample locations. How many people you combine VW rays with R matrix op at this point and kind of know what I'm talking about? All right, so I should give a little background here. The idea is that R flux matrix will tell you for a given set of points what the coefficients are to, say, the sky vault, right? The patches in the sky. A lot of people will use it with the luminance value. So you have these points in your scene that you want to know the luminance or the radiance at different times of year, and you want to run an annual simulation. You have these work plane points or something. That's what you'll give to our flux matrix normally, is the work plane points, and it will give you the coefficient matrix that corresponds to the work plane point. This is the same, only instead of work plane points, we're giving it the rays corresponding to an image. We don't use the dash uppercase I option. We leave that off, and it interprets these as desired radiance ray, evaluations. And VW rays just creates a collection based on a view. So it's essentially doing generating one picture per sky patch that corresponds to the say I want a rendering of this space in an annual simulation. I would generate the list of rays that correspond to my scan lines over the whole scene. So however many that is, 1 million or so rays. And each of those rays gets turned through our flux matrix and generates an image that corresponds to a particular patch's contribution to that view. And then it's a simple matter subsequently to take the different patch values for a different sky and use them as multipliers on the images, sum them all together and get a result. That is the view that you would get on a certain day and time in the year, usually driven by a weather. So we're doing the same thing here. We're using VW rays, generating that set of rays, typing it into our flux matrix, and down the command line somewhere there's this little dash that says, read your sender rays from the input. I want a floating point output. I want some feedback, how it's going. These resolution values have to match. Sometimes you use the VW rays -D to make sure that's true. I happen to know it's true in this case. The output is going to be put into this spectral view matrix with the R4 corresponds to the Reinhardt sky subdivision. So that will be set in this Reinhardt4.rad file. Bunch of rendering options to get a good result. And then the only option that's really different from a normal run is this -CS20. I'm saying I want 20 samples over the spectrum rather than 3. And there's no other thing to specify. It just does it at that point. And then number of processes. And that's input file specifies this Reinhardt4 sky here in the special comment. And then here's this, I just have the opening in the ceiling is my receiver surface. So it just uses the sky directions because it's just an opening. So we don't really need the sky at all. So that's the input to our flux matrix. And out of that, you get this good sized 20 component per pixel matrix. Since the output is a matrix rather than a set of images that you would normally use with a DC time step, now we have this huge single output file. This is the header for the output file. I don't know if you can read this, but it says number of components is 20. Number of rows is 2,330,624. So that corresponds to 1 row per pixel. And then the number of columns is 2305. That corresponds to the sky patches minus the ground patch for Reinhardt sky, because we just had the opening in the ceiling. We didn't bother with the ground. Normally you would have a separate ground, which would be a single coefficient. And then format is float. Seems to be missing something. Oh, so if you were outputting 2 images, you would add a %D here, and then each image would get its own output file or matrix. That's what you normally do when you're doing these view components. So if you're generating images, you generate a whole stack of images, and then DC time step reads in the stack of images 1 image at a time and does it efficiently. Yeah. Instead of that, you have one huge matrix output file that you then have to split into images. And I'll show you how that's done. It's a little awkward, but it works really well.
It also makes sense for
Yeah, you'd have to use R split again to get out the pixels into an image, but you could do it that way. DC time step works really well with images, so I'd continue using that method since it's available, but it just doesn't work with hyperspectral, unfortunately. I think this is missing something. There's supposed to be the wavelength partition thing, which is added by our Flux matrix. So I must have put this in earlier. So as I said, this number of rows corresponds to 1 row per pixel. And the 2305s, the Reinhardt patches minus without a ground patch. So this V matrix gets multiplied by a sky matrix, which has 1 row per sky patch and 1 column per time step. And that's the output of Gen S sky, or I mean, sorry, Gen S day matrix, or yeah. In my case, I was manually assembling this before Canning came up with the tool to do it. The R matrix op tool would need to load this huge 800 gigabyte matrix to do an operation in memory. So yeah, that kind of crosses that off our list of potential tools to use. But RCOM does a row at a time. We tell it, in this case, I'm running 8 processes. It took on my wife Elizabeth's modern Apple Silicon laptop, it took, I think, a day and a half or so to do this with 8 processes. On my laptop, it was never going to finish. So I gave it to her laptop to do because it's a lot of multiplies. It's just a boatload of multiplies to get all these spectra together. So running that big matrix a row at a time and using and concatenating with the sky spectrum matrix, we output a single, not an image, it is an HSR format, but it's like all the images in one file, but as this common exponent format, so it doesn't take up all my disk space. And then each row in that matrix is a new pixel position, and each column within a row is a different time step, so a different output image we want. We want to take all of column 0, put it in one picture, all of column 1, put it in a second picture, and so on. So we have completely the wrong ordering for doing that efficient in a normal tool, but we can use this R split to do it. So to use R split, unfortunately, since R split doesn't have a notion of what a picture is, you need to create a whole bunch of these info headers, which are essentially the preamble for each picture. So Radiance formats are pretty simple. They have a set of ASCII header lines and then data after that. So that the get info header the header info that you read with get info is just any lines up to a first empty line. That is the header. That's the definition of the end of the header in Radiance. And then in image files, additional resolution string, which tells the columns and their ordering. So that's what this line is. You create this file, and then you make, in my case, however that many copies of this file, of this header in a different file. So that's like the start of all of your images. And you just use a copy command or something like that to create this with a loop.
Is that you need to manually create?
Right. Yeah. So I had total of what 2304. No. Gets multiplied together. I forget how many times there are. It's like 4,000 or something. I took all of the time steps that had sun above the horizon for a year, I think. Oh no, I'm sorry. In this case, I'm just doing a day like half minute increments, whatever the SkyCam captures were, 30-second increments. So in this example, I'm doing it 1 day. So it's important to include this dimension string, and I just have an example of how you use a for loop to create all these. And then the rsplit command is the one you want, and you're telling it to read in an information header and a resolution string from this skyframes.hsr file we created earlier, this huge monolithic file that contains all of the time steps for, well, in this case, a day, and then split it into 21 byte increments. Why 21? Well, it's 20 components plus 1 common exponent. That's how many bytes a pixel is in this file. So for every 21 bytes, this gets expanded into a full list of steps. And how many steps there are, but I create 1134 steps. So that's 1134 files that get tacked onto that command line, and we're appending each of them. So it's a pretty simple command in the end, but it's a long command. And I actually had to modify rsplit to handle that many files. I think the limit originally was 512, and I just changed it to dynamically allocate however many it needs. And if you run up against the system descriptor limit, then it fails. But that limit's pretty generous almost. You sometimes have to run a command to tell it to unlimit the descriptor count for a file, for a shell. You guys can figure that stuff out. So as I said, 21 bytes corresponds to 20 components plus 1 common exponent. And then there's a result. So this is a time lapse. I think Andy posted this on LinkedIn of the SkyCam captures for an interesting day. Where was it exactly? Pennsylvania. So near Allentown, Pennsylvania. And it's half-minute data. So it's 900 times sped up here. You can see, you can feel, or it seems like you feel the clouds passing overhead, affecting the SkyCam captures. And so in effect, the open skylight is as an aperture, and it's kind of a camera. Yeah. Yeah, so that was days of calculation, just so I'm running it twice. Any questions at this point? I know it's kind of a lot. It's totally possible, especially on modern hardware. Things have gotten fast enough, and memory, I mean, I'm using an SSD, so the access time is not an issue. And it's doing things serially. That's the nice part. It's never got all this stuff in memory. It's doing everything serially. So even rsplit is just loading, and writing to one of its whatever 1,000 files at a time. Yeah. And what I usually do is I just plug in an external SSD and I use that. And I have one in my pack here with all the data on it in case anyone wanted to look at it. but yeah, you definitely want an external drive. That has the advantage of being able to unplug it and move your problem to a faster computer, which is exactly what I did. These are Macbeth colors. So the Macbeth chart has been measured many times. They even supply the spectra of the patches on the Macbeth chart. So that's what I went to I mean, obviously it doesn't handle some special case you have. You have to go out and measure those spectra. So that's pretty much it, yeah. Well, sometimes it's not 1, 1, 1. Sometimes it's a multiplier. Like I'll use the solar spectrum as a generic. This is what I want the solar spectrum to be. But then I'll plug in the radiance of the sun for a particular time of day and year. So usually they're the same, but they may not be one. So if we wanted to add electrochromics to this result, we'd get the spectral transmittance for different EC control voltages, which I did from Andy and Halio's EC system. We need to set it to something, so I don't have a virtual illuminance probe or sensor in there to tell me how to set the EC, so I just used an average of wall values. That was easiest for me. And then figure out what control voltage to apply to get the desired average luminance for that masked area. And then finally use the control voltage to compute the transmission spectrum for each time step. And then we can just post-process all our frames because it's just a multiplier on the window transmittance. And since that's the only source of light in this particular scene, I can just multiply the result. I don't have to do everything over again. So here's the heliospectra versus transmittance values. So we're plotting, these are microns, I guess. And this is a transmittance value for different target transmissions, which correspond to particular control voltages as well. And then we use a mask for averaging. So I just pick the back wall and the floor as my mask, and I'll average my luminance. I'll average my luminance values over that area, and then use that to decide what control voltage, how much I want to darken the opening. This ended up being my transmittance setting over the course of the day to manage the light. Since the sun was going behind clouds, in and out of clouds, there's a lot of spikiness there where it's like shutting the window down and then opening it up. And I didn't add any time constants or anything but it's supposed to be pretty fast, right? Not that fast. 3 minutes. Yeah. I don't know what 3 minutes is on this chart. Obviously, we're going over the whole course of a day. But since this is just an exercise, I mean, you can add bells and whistles to do it more sophisticated. But I have this mapping of values that are used in a loop. So there's the rcom command again. I'm not going to explain this because I don't even remember what I did exactly, but it's essentially taking the transmittance data and applying it to get the final frames. And this is all done in RGB after some point it's converted to RGB. So after doing the spectral multiplication, I convert the result to an RGB image because I'm just doing an animation of it anyway. So that's why I chose that. So this is a kind of a fun animation. This shows what the transmittance is. So the maximum transmittance is 80% or something like that, 60%. So that's showing 60% transmittance. And that sometimes of the day, it goes down, and that's where it's trying to block some of the light and decrease the transmittance. So you'll see that happening in the afternoon in particular. And this line going back and forth is showing the difference between a full spectral calculation and a standard RGB calculation. I've got this, it's a busy animation. But I ran a number of different experiments of how could I do this, and this one's the one I like the best. So that's the one I'm showing. But you can see at some times of day, there's a more significant difference than other times of day. And it does matter what the electrochromics are set to as to whether the spectrum makes a big difference or not. But it just shows the whole process can work. Like I'm just testing this end to end to see if it can even be done. That was fun. So we might also want to know what the relative luminance error is, comparing RGB rendering to spectral rendering. Here you can see the ratio. So 1 means means 0 error, and towards red means that the RGB calculation is running high. Towards green or blue shows that it's running low, or it might be the reverse. I forget which way I did the ratio calculation. But this is for photopic luminance over the course of a day. You can see it's within about 20%, even with RGB calculations. But 20% is kind of the limit of where we want to be with daylight calculations in the first place. So this definitely gets us more accuracy. And then we have melanopic error, which ends up being larger than the photopic error was. So that lends credence to people's belief that melanopic is a little more sensitive to spectral than photopic. It does seem to be from what I've seen. Any questions? Yeah, Robert. Color rendering meaning what exactly? Oh, color CRI. CRI. I have not tried that. That's a really good question. You'd probably start with, yeah, you might use spectral luminance, but yeah, spectral luminance, then apply the patches. And someone's working on newer methods for CRI that are much improved. Are you familiar with this, Rob?
TM metric and melody ultimately.
Yeah, CRI is a bit antiquated at this point, and there are reasons to not trust it, especially with highly spectral sources. Yes, the new methods take the same data, they just use a different set of sensitivity curves. And instead of using just instead of using test patches, they have a whole set of, it's more continuous, that's all I remember. Is that right? I'm not sure. And then there's Tunning's new Gen S Sky and Gen S Day matrix tools. So Gen S Sky, and Tunning, yell at me if I get this wrong, creates an HSR image of the sky based on atmospheric scattering simulations. Nods over there. Gen S Day matrix does the same, but uses weather tape as input, and there's a new option to the EPW to WA that grabs out the aerosol data that's needed for the calculation. Right? So simple example, similar run to Gen Sky. It specify a year or not. What is the dash F option? File names. Oh, right, because it works a little bit differently than Gen Sky. You create some temporary files that have to go someplace, and it names those files based on the dash F option or it defaults to something if you don't specify that. You can specify a number of processes, and the reason you'd want to do that is that the initial table generation is kind of expensive. It will only do it once in a certain directory, and I wanted to talk to you about like making that shared among different runs or whatever. But it'll only do that once for a given set of conditions. And what are the conditions? That they're not time of day and year; they're the aerosol conditions, right? Also time of day. Okay, so you need a different table for a different time of day. Oh, different seasons. Okay. I'm not up on all of this, but essentially it stores those tables in a subdirectory and reuses them for when it can in that directory, in that folder. So that takes time, and you can run it on multiple threads using the -n option if you have multiple processes, which most of us do, multiple processors. But then once it's done the tables and you're generating like the next time step or something, it's so fast you don't even need the extra processors at all, and it doesn't use them anyway. And then latitude, longitude, so standard meridian. This corresponds to Salt Lake City a few weeks ago. So the output of GenS-Sky is a custom calculated spectrum for the sun based on atmospheric condition. That gets applied to the solar light, and there's the sun. And then it defines skyfunc just as GenSky or GenDaylit would. It defines its own skyfunc, which is based on a spec pict that is this HSR output it generated and a fisheye mapping. Did I get all that right? And that's an example. It's an equirectangular projection. Yeah. So it's a fisheye, but it's a nice square, and it solves the problem we were having at the horizon because you initially had two hemispheres and it was not blending well. Yeah, so it's pretty easy to use. I highly recommend you try it. And then you apply it to the normal sky dome that you would for GenSky or GenDaylit. Then GenS day matrix goes from a weather tape, as we said, with the -A option. You can get out the additional aerosol information that you need for each time step. It also has a -N option. It uses the same trick of generating tables that it reuses for similar time steps. So this matters the first run. It doesn't matter for subsequent runs. And yeah, it's fairly efficient. It doesn't take that long to run. Initially it did because there was some reloading that was happening that we fixed. And then it just gives you the spectral sky data matrix, which you can apply with RCOM. In this case, I'm taking that spectral sky matrix and I'm applying it to the calculation I did earlier for our little room with the skylight. And I'm piping the output of that straight into RSplit and using the same trick to generate time step hyperspectral radiance pictures. So that will generate, because I use the -U option, which just says get times when the sun is above the horizon, I'll get half as many as you would normally get. So like 40, a little over 4,000 time steps. All right. So I have 4,000 time step files, HSR. And this is similar to using the RGB, the spectral sky, but instead of a continuous image for the sky, we have this patch-based representation. And in this case, we're using the Reinhardt 4 patches again. RCOM uses that V matrix that we computed before. And so I didn't talk about this, but the V matrix took about 12 hours to compute, I think, on an old 12-core Mac Pro. So it didn't take that long. It's a big file, but it didn't take much longer than it would normally take. And then RSplit divvies the results into HSR frames. So here's the result. This is speeding through an entire year instead of one day. I don't know what the time lapse. So this just, again, shows end to end the process works. More proof of concept than anything else. this run or the set of frames took, I think, closer to 2 days to run on my wife's laptop because it's more frames, like almost 4 times as many frames. Any questions on this part? We're getting towards the end here, in case anyone's running out of steam. Yeah. I was not making an effort on that in that direction. I used the same histogram for the entire set. So I used phisto to generate one histogram and then applied that using pcond on every frame. So you got the same. So we're seeing the variation in lighting. If we tone mapped individually, then it would tend to average thing, balance things to the same level, which you don't want. But it's a good point. It's like, how do you want to visualize the spectrum? I think you can use some imagination there of like daylight equivalent hours or something that you want to visualize. That would be more of a summary kind of thing. No, yeah. Well, Halio is not that spectral. It had some drop in the blue end of things, so you could say it's a little yellow, but it's not strongly yellow, is it?
A little brown.
Brownish in the dark. Mm. Oh, right, because there's a gradual rise and then a drop. So we discussed earlier with Robert and David about extending the spectral bounds. We use in all these examples, we essentially are doing 380 to 780. Extending that to the near infrared works fine, but once you're in the thermal IR, that's in the 3,000 to 100,000 nanometer range, which is really hard to balance with a uniform step size. And that is an issue. Like I said, frequency would make a lot more sense in terms of physics, but it conflicts with all the current measurement methods and the data that we have available. So kind of stuck in this place where we can't do what makes sense because everyone did the other thing already. Yes, to do it properly. That's also a problem. You can still do optical ray tracing, but you have to have the temperature of each surface and know how it radiates. Yeah, we don't have a good solution for that. We don't even have a convenient way to specify a reflective surface as an emitter. You have to use a mixed func or something. This is one of the advantages that we could have gotten from moving to more of an MGF model, is that it's very flexible with its material specifications. But like I said, because it's so flexible, we'd have to rewrite a lot of the core routines in Radiance. So, any other questions? We reached the end. My little seminar tutorial that you guys didn't have to get your hands dirty for.
This is really exciting, Greg. Thank you for taking this on. Others that have taken. I understand the daylighting world, which is not my domain. Electric lighting, I don't believe electric lighting world. In architecture, it doesn't have to be theater, it doesn't have to be film. I mean, we used to have like RGB, 3 emitters in a node. And that's now expanded to maybe 4 at a W. And for other purposes, they're up to maybe 7 emitters in a dome of red, lime, amber, green, cyan, blue, indigo, and some way to represent these. And also to be able to color mix them. That's what we do with those variables. And even the simplicity of warm dim, when you've got, 200K emitter and a 3500K emitter, which is common in architecture. And meshing all this with what's happening with the daylight spectrum just opens up this tremendous opportunity for practice. and all the work ahead that you've got to do what I just said.
Yeah. Well, actually, it's not that hard to have these multi-component light sources because each one can be a channel in our flux matrix calculation. And then you can, go to town with your settings and see what it's like in pretty short order. I mean, you probably have to have some specialty tools to see it in real time, but.
Yeah, and just a simple question. I imagine that an HSR image format is viewable through something like Exhibit.
That would be nice. No, you have to use the R code to BMP to get a BMP out of it, and then you open it with whatever tools you have. Can I automate it for Excel? Yeah, we should probably have a converting input, but I have not written. Any other questions or feature requests? Yeah. So I thought about this, but I tabled it for later. I had too many other things to work on. Malika? It's equal through the whole spectrum, so it's going to be however many nanometers it works out to as increments from the start to the end. And then as far as the RGB channels, it's divided by those partition points that I mentioned, and that actually gets written into the output. It's technically possible to change those partition points and say I want different partitions for RGB, but that's just used for places where you've actually specified a material RGB value or some other RGB value that's supposed to multiply the spectrum. Then that's when that partition comes in and says, this will multiply this part, this will multiply this part, which is a hack, really. But it's the hack that enables this whole thing to work. So. This, yeah. Yeah. Cool. Anybody else? All right. Yeah, thank you.